Recording is rolling for Thursday, October 21st. I know the last few days I've been telling you guys all about energy and energy conservation, a little bit about power. Been doing a bunch of notes, a bunch of examples. So, thinking last night, you guys probably need a lab day to get back there and work with your friends and get your hands on some of those materials. So, I've got a mechanical advantage lab for you guys, pulley systems. So, a pulley system is one example of a simple machine. A simple machine you can get what's called a mechanical advantage, and that's what you guys are going to be measuring, calculating today. Uh, so mechanical advantage is something where you can have a small input force and get a very large output force. So it's kind of like multiplying your strength. But this is also going to, once you make some force and distance measurements, uh, confirm a conservation of energy. Right. So I've got a 3-to-1 mechanical advantage pulley system rigged up here, but I have a live version of a 5-to-1. So let me turn the camera for the video, point up the 5-to-1. All right. Right, so you guys see, oh, right, I see some pulleys, I see a bunch of strings, I see a 1 kilogram mass here that weighs almost 10 newtons, like 9.8 newtons. And then on the other end of the string system, I've got this spring scale and a very small mass. This is only 200 grams, that's about 2 newtons. But damn it, how's the 2 newton guy pulling down and the 10 newton guy get pulled up? How is that possible? Well, something to do with how the strings are wound around these pulleys. Do you guys notice that the top two you guys do see 3 red pulleys, right? The top 2 pulleys are fixed. They're fixed in place. These guys are fixed pulleys. They're not moving. But this bottom one, different story. See how the bottom pulley is moving up and down with the big weight? Is that okay? So that one's a movable pulley. And when you guys are rigging up these systems, you're gonna have some fixed pulleys and maybe a movable pulley, depending on your design. Oh, and salvage. Okay. All right, so let's go back to the pop the string back in this groove. That's part of the fun today is getting getting the string into those grooves. All right, so switch back over to this page so I can point out what the physics is behind this. Now, the one I just showed you is a 5-to-1 mechanical advantage, but this is only a 3-to-1 system. Oh, sorry, one more thing with the 5-to-1 that I want to prove to you guys. Camera switch real fast. So this weighs about 10 newtons. What is the actual force reading on the spring scale? It's only reading about 2 newtons. If you can see the newton marker, it's 2 newtons. So essentially, it's a 2 newton force on this end, holding up a 10 newton weight. And what's the ratio of those forces? 10 newtons divided by 2 newtons. Isn't that like a 5-to-1 ratio? Like 5-to-1 ratio? And there are, like 1, 2, 3, 4, 5 strings emerging from this movable pulley, pulling straight up. Right, so, okay. How does that translate to simpler, like 3-to-1 mechanical advantage system? Well, look at how the strings wound around. You guys see the movable pulley, there's 1, 2, 3 strings pulling up for 1 weight pulling down. So it's kind of like this weight's being supported by 3 strings. So its weight is divided into 3 parts. So the tension in each string is like 1/3 of the total weight. Is that? But it's actually all the same string, isn't it? It's just like round. Okay. So by the time the tension translates over to the input side, and here's the input side where you're like pulling the spring scale, you effectively only get like 1/3 of the force, right? So yeah, so you can lift something very heavy with a very small input force. But you don't get something for nothing. You're paying for that with the distance that you pull, because you could pull lots and lots of string on this side, and that distance also gets divided into 3 parts. So here's the conservation of energy approach. So energy being conserved, whatever work that you put in, that's the maximum work that you can get out on the other end. Right? So like input work, output work, and work. Well, that's force times distance. You guys remember? Remember work is force times distance. Right? So the input force, which might be very small, times the input distance, which might be very large, is equal to the product of force and distance on the other side. It's a very large output force, but very small output distance. Okay? So I've labeled the forces and distances for each one of these. Right? So see, small input force, but a long distance that you pull is like maybe like 30 centimeters. So this very large weight might be about like 10 centimeters, like that. Okay? So you can pull a very big weight, but just a little bit at a time. Then what about this whole like 3-to-1 mechanical advantage ratio? There's actually 2 perspectives on mechanical advantage. ideal mechanical advantage is the ratios of the distances. So what's the input distance versus the output distance? My example on it might be like 30 centimeters versus 10 centimeters. I pull 30 centimeters, this whole thing moves up 10, 30 to 10, that's a 3-to-1 ratio. Okay? But then there's like real mechanical advantage, like actual mechanical advantage. What advantage are you actually getting? How much are you actually multiplying your strength? Well, that's a force ratio. The output force divided by the input force. So in this case, if this weighs like 10 newtons, and you might need like 3.3 newtons to pull it, then you divvy those two. It should be pretty close to 3-to-1, but realistically, it might be a little bit less than 3-to-1. Like maybe maybe it's only like 2.5-to-1, something like that. Why would this be? Why do you think real mechanical advantage would be a little bit less than ideal? What would cause that? I think maybe possibly a little bit of friction in the pulleys. Maybe if these strings aren't straight vertical, there's a little bit of a trigonometry aspect to it. Maybe reasons like that. Right? Actually, if you want to calculate efficiency, you can do that too. It's just the ratio of those different mechanical advantages, real compared to ideal. You just divide those. So it might be like 92% efficient, something like that. Right? You guys get that? Okay, so I have a lab page for you guys. Now, got just a few dollars left in my print budget this month, so you guys are gonna have to share these. But it's gonna look like this. I'll go over this with you guys so you know what's going on. This lab is in 4 parts. I'm gonna have you guys construct lots of pulley systems. So there's a one-to-one mechanical advantage. So one-to-one mechanical advantage. So you guys can see that. Okay. The next one, do a 2-to-1 mechanical advantage, then a 3-to-1 mechanical advantage, and a 4-to-1 mechanical advantage. So I have a 5-to-1 rigged up live in class. You can get your hands on it. Can you see it? And here's the 3-to-1. I'll leave that picture up here over the course of the lab. Draw one of these for you guys. So in this blank space here, draw it. So I'll do the one-to-one for you guys. One-to-one isn't really a huge advantage, just like rerouting the direction of the force. Right? So you might have a lab weight on one side, you have a spring scale on the other side, okay? And whatever the output force is should be the input force. But then here's where you actually make the scientific measurements. So I gave you some boxes to make measurements and calculations. Yeah, in retrospect, looking at it this morning, I should have arranged these boxes a little bit differently. Could have done a better table layout, but that aside, whatever your weight used is, guys, what is weight measured in? Newtons. Okay. And then the force rating on the other end, say the spring scale end, that would also be in newtons, right? Okay. Now, if you divide those two force ratings, you'll get the actual mechanical advantage, which would be maybe it's like 1-to-1. Hopefully, it should be pretty close to 1-to-1. Okay. Height change. So as you pull the spring scale down, that'd be the length pulled, might be some number of centimeters. That weight is going to move up some number of centimeters. And for the 1-to-1, it should be exactly the same. It might be like 10 centimeters you pull down, 10 centimeters the weight moves up. Okay. So that would be the ideal mechanical advantage would be 10/10, would just be a 1-to-1. Okay. So the challenge for you guys today is, can you construct these different pulley systems? Can you measure distances and forces? I did get a question how to measure distances earlier. Okay. Because forces, well, you just grab what is the weight of this in newtons and what is the, you might hang it from spring scale directly. Okay. And what is the force rating on the spring scale? So forces is pretty direct. Now the distances moved, you have to be a little tricky about this. You might need 2 different rulers or 2 different meter sticks, and you're looking at how far does this one move up, how many centimeters versus how far do you pull down, how many centimeters. That would be like input distance and output distance. Okay, so I need a couple of rulers for that. Okay. And so can you break up these systems? Can you measure forces and distances? Can you calculate ideal and actual mechanical advantage? And make sure that all your names are on this page. I'll pass some of those out. And just pop that in the grade tray by the end of class. Okay. And then tomorrow we'll chug through as many textbook problems as we can. Okay. Who's got any questions? Any questions? All right, you guys got the rest of class.